So we talk a lot, right, about cutting new carbon emissions, and that's absolutely vital, of course. But think about all that historical CO2,
Yeah.
the billions of tons already up there warming things up, trapping heat. The truth is, well, to really tackle climate change, we have to actively remove it from the atmosphere. And that just feels like a monumental challenge.
It really does.
And often, when we hear about climate solutions, our minds jump to these huge, expensive, almost futuristic technologies.
Yeah, the big silver bullet ideas.
Exactly. But what if some of the most powerful answers are actually kind of hidden in plain sight, maybe, by looking at existing problems in a whole new way?
That's a really interesting angle.
So today we're doing a deep dive into this fascinating research paper. It proposes a novel and potentially incredibly scalable approach to carbon removal.
Yeah.
And it uses a really unexpected pair. Tiny plants and, get this, abandoned oil wells.
An unlikely duo for sure.
Our entire deep dive today is based on this detailed paper. It really digs into the technical side, the economic feasibility of this new pathway, specifically focusing on the U.S. context.
Right.
And by the end of this, you'll hopefully see how this approach could, maybe transform a massive liability. We're talking hundreds of thousands of abandoned wells into a powerful environmental asset.
Turning a problem into a solution.
Exactly. And also how building many small units, this idea of economies of numbers, might just be more potent for this kind of climate solution than building one gigantic one. So let's unpack this.
Sounds good. Where should we start?
Let's start with just the sheer scale of the climate challenge. We've all heard the warnings, but I think it's worth revisiting the numbers just quickly. Human activity has sent atmospheric CO2 just soaring, from a stable 280 parts per million back in the late 1700s.
Before the Industrial Revolution, basically.
Right, to 419.3 parts per million in 2023. That's not just a number. We've fundamentally altered our atmosphere in a geological blink of an eye, trapping heat like crazy.
It is stark. And the IPCC, the Intergovernmental Panel on Climate Change, they projected in 2023 that global surface temperatures, they'll likely exceed 1.5 degrees Celsius warming within just 2 decades.
2 decades, wow.
Yeah, if we don't take really significant action, and this underlines a critical point, just cutting new emissions, it isn't enough anymore.
Yeah.
Not to stay below that threshold.
So we have to pull the old stuff out.
Exactly. To truly mitigate the worst impacts, carbon sequestration technology actively removing that historical CO2, it's really presented in the literature as, maybe the only option to achieve that goal.
Okay, so removal is non-negotiable. What are the current sort of main ideas out there, and what are the catches? Like nature-based solutions. Planting trees, reforestation.
Right, afforestation, reforestation. On the surface, they sound perfect, don't they?
Yeah, totally. Seems cheap, too.
They are relatively inexpensive, yeah. The paper mentions costs around $0 to maybe $20 per ton of CO2 removed.
Okay, that's cheap.
But, and it's a big but, their limitations are pretty significant. These natural solutions, they're slow. It takes time for trees to grow and sequester carbon.
Right, decades.
And you're limited by land availability. You can't just plant forests everywhere. And crucially, they're vulnerable.
Vulnerable how?
Wildfires, pests, droughts, things that are actually getting worse with climate change. We've seen huge wildfires just release all that stored carbon right back into the atmosphere, undoing the work.
Okay, so nature helps, but it's slow and risky. What about the high-tech end? Direct air capture, DAC.
Ah, yes, DAC. Pulling CO2 literally right out of the thin air, creating a pure stream you can store underground.
Sounds amazing, like science fiction.
It is amazing tech, definitely exciting. But the challenge with DA isn't really can we do it, it's more can we do it affordably and at the massive scale needed.
The cost?
Exactly. It's incredibly energy intensive. We're talking up to maybe 17 kilowatt hours of energy just for 1 kilogram of CO2 captured. That's a lot of power.
Wow, and the price tag.
It's one of the most expensive options. Costs range hugely, actually, from maybe $93 up to potentially $1,000 per ton of CO2. Very wide range, depends on the specific tech and energy source.
Okay, so very expensive. That makes these hybrid approaches seem more interesting, right? Using plants like nature, but adding technology.
Yes, exactly. These use plants to capture the CO2 first, then they process that plant material, the feedstock, using technology.
I think I've heard of BCCS, bioenergy with carbon capture.
Right, BCCS is one, but the key difference there, and this is important for today's discussion, is that BCCS is primarily about generating energy from the biomass. The carbon capture is almost like a a secondary benefit, often incentivized.
Okay, energy first, carbon second.
Pretty much. But this paper shifts the focus entirely. It's centered on something called BiCRS, biomass carbon removal and storage.
By CRS.
Okay. And with BiCRS, carbon removal isn't the side benefit, it's the main event. The whole process is designed from the ground up to maximize carbon removal. Full stop. While trying to keep costs down, of course.
Carbon removal first.
That's the goal. And among the different ways to convert biomass, fast pyrolysis, it's getting a lot of attention.
Why pyrolysis specifically?
Because it can be done efficiently at a smaller scale, a more distributed scale, which is a huge advantage when you think about where biomass actually is. It's spread out, right? Fields, forests.
So you'd process it near the source. Makes sense.
Exactly. Avoids hauling bulky biomass long distances.
Okay, so with that context, BiCRS focused on removal, using potentially small-scale pyrolysis. How does this paper actually propose we do it? You mentioned pyrolysis and orphaned wells.
Right. So let's break down pyrolysis first. Fast pyrolysis.
What is it exactly?
In essence, it's a rapid heating process. You take biomass, could be plants, wood waste, agricultural leftovers like corn stalks, and you heat it up really fast between, say, 400 and 700 degrees Celsius, but crucially without oxygen. It's a thermochemical deconstruction.
No oxygen. Got it. What comes out?
Three main things. A liquid called bio-oil. It's kind of like a crude oil, but made from plants.
Bio-oil?
A gas, which contains energy, and a solid, known as biochar. Think of it like charcoal, but made under specific conditions.
Bio-oil, gas, biochar. And here's the innovative part, right? What they propose doing with that bio-oil.
This is the key leap in the paper, yeah. Typically, you might try to upgrade that bio-oil into, say, transportation fuel.
Right, burn it.
Right.
Which releases the carbon again.
Exactly. It puts the carbon right back into the atmosphere eventually. But this paper says, what if we don't do that? What if we produce this bio-oil specifically for permanent storage?
Permanent storage.
Where? By injecting it deep underground, specifically into abandoned or orphaned oil and gas wells.
Ah, the other half of the equation.
Right. This design choice maximizes the carbon removal because that carbon in the bio-oil stays locked away. And it has a neat side effect. It frees up the biochar.
What happens to the biochar?
It can be used as a soil amendment, which is great for agriculture, improves soil health, water retention, and it also keeps its carbon locked in the soil for a long time. So you get a double carbon benefit, potentially.
Okay, that sounds pretty clever. So the overall system, how would it work? You mentioned distributed.
Yeah, the paper proposes a distributed network model. Imagine maybe 200 small-scale pyrolysis biorefineries. Not one giant plant, but many smaller ones.
Located where?
Strategically placed near the biomass sources themselves, near farms, near forests where waste wood is available.
Close to the feedstock.
Exactly. The idea is you convert the biomass right there on site into the bio-oil, biochar, and gas.
Using that 400, 700 degree process.
Right. Then, that liquid bio-oil, which is much denser and easier to transport than the original biomass, gets shipped to a central terminal for storage.
And from there?
From there, it's transported to the final carbon storage locations, those orphaned wells. It's all about bringing the processing to the raw material, not hauling bulky stuff all over the place.
Which brings us to this hidden opportunity, orphaned wells. The numbers you mentioned earlier are kind of shocking.
They really are. As of April 2022, the official count was over 123,000 documented orphaned wells in the U.S.
Documented, meaning there are more.
Oh, yeah. Estimates for the undocumented ones, they range wildly, from maybe 310,000 up to possibly 800,000 wells, just forgotten, often leaking.
It's a massive environmental liability.
Yeah.
Leaking methane, potentially contaminating groundwater.
Exactly. And dealing with them the current way is incredibly expensive. There was funding allocated in the Infrastructure Act, right, to close about 120,000 wells.
How much does that cost?
The estimates are around $1 million per well.
$1 million per well.
Yep. And it uses billions of gallons of water or sometimes oil-based fluids just to plug them up in the traditional way. Huge cost, huge resource use.
Okay, but here's the genius part, right? Injecting the bio-oil instead.
This is where it gets really interesting. Bio-oil can be injected directly into these abandoned oil and gas fields. I mean, think about it.
They already held oil and gas.
For millions of years, these geological formations are proven, secure storage sites. They're naturally designed to hold hydrocarbons without leaking.
Makes perfect sense.
And there's another potential advantage. Bio-oil is generally denser than the crude oil that was originally there.
Denser. So it sinks.
It tends to sink within the formation, yeah. Which could actually enhance its long-term stability down there, keep it from migrating upwards.
Wow. And are there rules for this? Safety regulations.
That's another plus. There are already existing regulatory frameworks like the EPA's Underground Injection Control Program, designed with safeguards, rules to prevent fluids from migrating, to protect groundwater sources. So we're not starting from scratch on the safety and oversight side.
Okay, so we have this massive problem, abandoned wells.
Yeah.
And we have this potential solution, bio-oil injection. Where does the biomass come from? You mentioned the U.S. has a lot.
A huge amount. Over 1 billion tons annually, potentially available. This includes things like agricultural residues, corn stover, the stalks and leaves left after harvest, especially in the Midwest.
Corn stover, okay. What else?
Forest residues, branches, treetops left after logging. Material cleared to reduce wildfire risk.
Ah, the wildfire connection. That seems really important, especially out west.
It's critical. A century of suppressing fires has led to this massive buildup of, fuel in our forests. Dense, overgrown areas just waiting for a spark.
Creating conditions for these catastrophic wildfires we keep seeing.
Exactly. Removing that excess biomass, that fuel load, is crucial for forest health and community safety. But historically...
It costs money to remove it, right?
Yeah.
And it doesn't have much market value.
Precisely. It often has low market value, and the transport costs to haul it somewhere are high. So it's often just left there, or maybe pile burned, which releases carbon anyway.
So BioCRS could change that.
That's the potential. This BioCRS technology using pyrolysis could actually monetize these forest wastes. How? Through carbon removal credits. Suddenly that waste material has value.
So it creates an incentive to clear the forests, and you get carbon removal.
Exactly. It's a solution that tackles two problems at once: wildfire risk and atmospheric carbon. And the potential scale here is, pretty surprising.
How much are we talking?
Just from forest biomass alone, the paper estimates around 720 million metric tons of CO2 could potentially be removed each year in the U.S.
720 million tons. How much is that relative to, total emissions?
To put that in perspective, it represents about 15% of the entire U.S.'s annual CO2 emissions back in 2023.
15%, just from forest waste.
Just from utilizing that forest biomass through this pathway.
Yeah.
It could be a real game changer if it's scaled.
Okay, that's huge potential. Let's dig into the mechanics a bit more and the money, the techno-economics, life cycle stuff.
Right. So the paper modeled a base case scenario, a small facility using corn stover as the feedstock.
Okay, corn stover. What were the numbers?
From about 10 dry tons of corn stover going in per day, the simulation generated around 5.3 tons of bio-oil and 2.5 tons of biochar per day.
And the process itself, what are the main steps?
It's relatively streamlined, actually. Starts with feedstock handling needs to be dried, ground up, screened. Then the pyrolysis reaction itself, heating it fast without oxygen. Then you have to recover the bio-oil, condense it out. And there's a smart gas recycling system. The non-condensable gases produced during pyrolysis, they're not wasted. They're used to generate heat for the process itself.
Oh, so it helps power itself, makes it more efficient.
Exactly. Makes the whole thing more energy efficient.
You mentioned the biochar has value too.
Yeah, that's another revenue stream helping the economics. The model assumes the biochar is sold for about $100 per ton, mostly for agricultural uses, soil amendment.
Okay. And transportation, you said moving bio-oil was cheaper than biomass.
Much cheaper. Transporting that densified bio-oil costs about 12 cents per ton per mile in the model.
Yeah.
Compare that to hauling bulky raw biomass, which is estimated around 90 cents per ton per mile.
Wow, big difference. Really shows the benefit of processing it near the source.
Definitely highlights that strategic advantage of the distributed model. Process it locally, ship the denser liquid.
So let's talk dollars and cents, the economics. The study mentions nth plant versus pioneer plant. What's that about?
Ah, right. That's a common concept in technology deployment. Think of the pioneer plant as the very first one you build. It's often custom, maybe has some kinks to work out, usually more expensive.
Prototype.
Essentially, yeah. The nth plant, where n just means some larger number, represents a mature version, like the 100th or 1,000th unit built. It's been optimized, standardized, benefits from mass manufacturing. It's more reliable and cheaper.
Okay, so you learn as you build more.
Exactly. And this is where learning rates and those economies of numbers become absolutely crucial for this kind of technology.
Economies of numbers, not economies of scale.
Well, both matter, but for these small modular units, the learning curve getting better and cheaper as you make more of them is really powerful. The study shows that with a 20% learning rate,
Meaning costs drop 20% each time production doubles.
roughly, yeah. That kind of learning can reduce the minimum selling price needed for the bio-oil by about 23%, and it cuts the marginal abatement cost, the cost per ton of CO2 removed, by nearly half compared to that initial pioneer plant.
Half, just from getting good at building them.
Pretty much. It strongly suggests that building many smaller units, leveraging manufacturing efficiencies, could drive down the costs really rapidly, much faster than maybe trying to build one enormous complex facility right off the bat.
So what are the actual cost numbers for this corn stover base case?
The capital cost for one of these small 10-ton per day facilities, surprisingly modest, estimated at $1.28 million.
Okay, $1.28 million. And the cost of removal?
The minimum selling price for the bio-oil needed to make it viable, that's calculated at a 10% internal rate of return, so it's a realistic business case, is $175 per ton of bio-oil.
Okay, $175 per ton bio-oil. How does that translate to cost per ton of CO2?
The resulting carbon abatement cost, the MAC, is calculated at $83.66 per ton of CO2 if you include the carbon sequestration benefit from the biochar going into the soil.
$84 a ton, roughly. That sounds pretty competitive.
It does. If you don't count the biochar benefit focusing only on the bio-oil injection, the cost is higher, around 152 tons per ton of CO2.
Still, $84 to $152. How does that compare to, say, carbon credit prices?
Well, those prices vary a lot, but these costs fall squarely within the range of proposed and even existing carbon credit prices in some markets. It suggests this approach isn't just technically feasible, but could actually be economically viable, especially as it scales and those learning curves kick in.
Makes sense. What drives the operating costs mainly? Is it the pyrolysis itself?
Actually, no. The biggest operating cost drivers are the biomass itself, purchasing it, collecting it. That accounts for about $87 per ton of bio-oil produced.
So getting the feedstock is the main cost.
It's the lion's share of the operating expenses. What's interesting is how low the bio-oil delivery cost is, just $3.01 per ton in the model. Again, showing that transport efficiency once it's liquid.
Okay, economics look potentially promising. What about the overall environmental footprint? Does it actually remove CO2 on a net basis?
That's a crucial question. The paper did a life cycle greenhouse gas analysis specifically for the corn stover case. And it shows a clear path to net CO2 sequestration. Yes, the corn grows, capturing CO2. Then you account for all the emissions during the process running farm machinery, the energy for pyrolysis, transport, the well plugging itself.
Even with all that accounted for?
Even with all that, you still end up removing more CO2 from the atmosphere than you emit. It's a net negative process.
That's good news. Does the type of biomass matter for the footprint?
Oh, definitely. The study compared different feedstocks, and generally woody biomass, things like pine, poplar, even waste wood like oriented strand board scraps, tended to have lower overall life cycle emissions compared to agricultural residues.
Lower than corn stover.
Lower than corn stover, and especially lower than switchgrass, which showed higher CO2 emissions linked to its cultivation and production in this analysis.
So the choice of feedstock really impacts the net carbon benefit.
Absolutely, and not just for carbon. The study also looked briefly at other environmental impacts, things like potential carcinogens, ecotoxicity, and there too, agricultural feedstocks like corn stover and switchgrass tended to score higher, meaning more impact, than the woody biomass options.
Interesting. So maybe focusing on waste wood or forest residues is better overall.
It seems to have advantages from a life cycle perspective based on the study. Plus, it ties into that wildfire mitigation co-benefit we talked about.
Right. Now, one really interesting finding you mentioned was comparing this to direct air capture. These small pyrolysis units are more economical at smaller scales.
Yeah, that was a fascinating takeaway. The analysis suggested that for carbon removal projects below a certain size, roughly 6,000 metric tons of CO2 removed per year, which is still quite significant for one location.
Okay.
These small distributed pyrolysis systems are actually more economical than DEDO. DX really needs massive scale to bring its costs down, becoming more competitive, the study suggests, maybe around $120 per ton CO2, but only at those very large centralized facilities.
So the advantage for pyrolysis here is?
You can achieve really large overall carbon removal capacities by deploying many of these smaller standardized units. You avoid the huge logistical challenges and massive upfront investment of trying to build one ginormous DC plant, or even one giant biomass plant that needs feedstock shipped from hundreds of miles away.
Less risk to brain.
Exactly. Investing in smaller modular units reduces the financial risk. If one unit has an issue, the whole system isn't down. It's appealing, especially for deploying a technology that's still maturing in this specific application.
Okay, it sounds really promising, but
Yeah.
no new technology is perfect. The paper must have mentioned challenges, limitations.
Oh, absolutely. And credit to the authors, they were very upfront about them. They acknowledge this is still an emerging technology specifically for the well plugging application. So there are uncertainties in some of the modeling, like exact future feedstock prices or how stable the carbon in biochar really is over centuries in different soils.
Standard modeling uncertainties.
Right. And then there are the big ones. The real-world scale-up and commercialization risks. Technical hurdles, financial challenges, and policy gaps.
Let's talk about those scale-up challenges. What are the big ones?
Well, logistically, bio-oil itself can be tricky. It's often acidic, can be unstable over time. It needs specialized handling, storage tanks, transport equipment.
Not like shipping regular oil.
Not quite. And our existing infrastructure roads, rail might face limitations if you're suddenly trying to move huge volumes of this stuff. Pipelines specifically designed for corrosive liquids like bio-oil, they're pretty scarce right now.
Okay, handling the bio-oil is one thing. What about the wells?
Injecting it isn't trivial either. You need rigorous assessments of each well's integrity. Is it suitable? Is the geology right? You need site-specific permitting for every injection. You can't just go pump it into any old abandoned well. Safety and environmental protection are paramount.
Makes sense. You also mentioned policy gaps. That sounds crucial.
This is potentially the biggest hurdle right now. Despite some real market traction, you mentioned Charm Industrial earlier, they've actually delivered over 8,000 tons of bio-oil for sequestration and sold credits for nearly 310,000 tons.
So companies are actually doing this.
Yes, it's happening. But this specific pathway, bio-oil injection for carbon removal, is kind of invisible, or at least underrepresented in a lot of major climate models and, more importantly, in key policies.
How so? Like the 45Q tax credit in the U.S.?
Exactly like 45Q. That's a major incentive for carbon capture and storage, but it currently doesn't compensate this form of carbon removal. Why? Because its language is structured around capturing and storing gaseous or supercritical carbon oxides, the kind of CO2 you get from power plants, industrial facilities, or direct air capture.
So this liquid bio-oil pathway just doesn't fit the current rules.
It falls into a gray area or outside the explicit definitions, which means companies doing this might not be able to access those valuable tax credits, making the economics much harder.
That seems like a major oversight if the potential is as big as the paper suggests.
It really does. And that's a broader implication here. This study provides really important foundational techno-economic data. It helps show policymakers the potential scale and viability of bio-oil sequestration.
So they can see it's a real option.
Right. And hopefully that can lead to updating policies, creating stable long-term incentives, maybe harmonizing standards for monitoring and verification. Those kinds of policy signals are absolutely critical to attract the investment needed to scale this up. Without that clear support, even really promising technologies can struggle to get off the ground.
Okay, so wrapping this up then. To recap our deep dive,
Yeah.
this idea, using distributed biomass pyrolysis,
Taking things like forest waste, agricultural residue,
diverting them into bio-oil near the source.
and then permanently storing that liquid carbon down in abandoned oil and gas wells.
It really seems to offer a promising, maybe even economically viable pathway for large-scale carbon removal.
Especially as the technology matures, costs come down through that mass manufacturing, the economies of numbers. It looks like a really valuable tool to add to our climate toolkit.
Definitely. And as we finish, maybe a final thought for you, the listener, to consider. What are some of our biggest environmental headaches? Things like abandoned, leaky infrastructure, or the growing danger of catastrophic wildfires. What if they actually hold the seeds of our most innovative climate solutions?
Yeah, it requires looking at them differently, doesn't it?
It really does. Seeing liabilities not just as problems to be cleaned up, but as potential assets, as opportunities. So the question to ponder is, what other existing problems out there could be repurposed, reimagined for environmental benefit?